for this demo, this is a classic demonstration of torque, and just a quick overview of what torque is that there's a little bit of a distinction between linear physics and rotational physics.
Okay.
So a force is what we talk about that makes something accelerate. It makes something start to move. It can speed it up, it can slow it down, it can make it turn. So forces make things accelerate, typically in straight lines. But in rotational physics, instead of talking about forces, something that makes an object start to rotate or accelerate rotationally would be a torque. And so torques are a lot like forces, but the difference is that instead of just mattering how hard you're pushing or pulling on an object, which is what a force is, a torque is measuring the force and the distance from the pivot or the fulcrum. So the classic example would be using a teeter-totter or a seesaw. If it's right in the middle, if it's perfectly balanced, then even forces on both sides. But once you start to shift and one side is longer than the other, the longer side is going to apply a bigger torque. The smaller side, even if it's the same weight, is going to be a smaller torque because there's less of a distance to that pivot. That's the basis behind most of the idea of simple machines like levers. You're getting a mechanical advantage because those distances are different, and so the forces affect objects differently. So on this particular demo, this is a classic demonstration of torque, and it's called walk the plank. What we've done is we've got this large board, and we know that this board has a mass of 20.5 kilograms, which is about 41 pounds. So 20.5 kilograms, and we know that its length is 3.67 meters. So we can calculate that the center of gravity on this board is right here, exactly in the middle, and we can basically approximate that the weight of this board is going to be a force acting down in the middle at the center of gravity. So the to the edge of the table is going to be the distance that the board's weight is acting. It's going to try and pivot right here along the edge of the table, and that's going to be our fulcrum. So the board, the weight of the board is pulling down on this side, and so it's trying to cause things to rotate in this counterclockwise direction. What we're going to have you do is we've calculated, based on your weight, that you should be safe anywhere on this side of the board, because even though you weigh more than the board, this distance is so much shorter that your torque, even all the way out to the edge, won't actually cause the board to rotate because it's being overbalanced by the torque going the other direction. So you should be able to safely walk the plank.
Okay.
Just because we want to make sure that we're proving that this isn't a trick, we're not actually doing anything nefarious, we're not trying to delude people, this board is not attached. It's just sitting on the table, it's very heavy, and what we have going on is we've just measured the correct distance so that the board won't rotate when she climbs on it.
Okay.
So if you want to go ahead and hop up.
And where do you want me to start? Like at the middle? Or?
Always safest to start at the center of gravity.
Okay.
There's no danger here, but as long as you're walking, once you cross this threshold, once you pass the fulcrum, you'll still be safe, but technically then your torque would be going against the board.
Okay. And even out to the edge?
Even out to the edge.
Okay. All right.
So, exactly like we said, your torque here, the weight of you focused right on your ankle bones is pulling down, and the distance here is not enough to create enough torque to rotate the board and overbalance it. You could even step further out with your toes fully hanging off, but that's harder to trick your brain into doing. Your brain knows this is a weird thing and I'm uncomfortable.
Okay.
But yeah, absolutely.
Yeah.